Okay, I'm going to talk about a topic from Chapter 3 called Modulation Bandwidth. And this is another way of characterizing our fiber optic system in terms of its frequency response. And what I'm going to do is I'm going to start off with the following. I'm going to start off with an input optical signal, and I'm going to then end up with an output optical signal after we go through our system. And what we're going to do is we're going to write that the optical power is a function of time, and we're going to have a modulated optical signal. In other words, we're going to start off at the input with some DC optical power times the sine of 2 pi ft. So we've modulated our optical wave. Don't confuse this with the actual electromagnetic wave. This is the modulation of an optical carrier, and we're modulating that carrier at a frequency f. On the output side, what we're going to find is that we have some output optical power, and I'll call it with a prime. It's a function of t also, but it's also a function of that frequency f. And what we're going to find is that we have p naught as a function of f times the sine of 2 pi ft. So essentially p naught is, and now we're going to write this as p naught prime because that is the output optical power. Okay, so we're assuming that there is no DC component here, so P naught is just that amplitude optical power, okay, of this modulated wave. What we're going to find is that the output does vary with the frequency, and I've got a spreadsheet that I'm going to go ahead and post that demonstrates this in the terms that we've already seen in terms of pulse spreading. So what we see in our system here, and we've talked about this in terms of pulse spreading, is that if you have too high of a frequency going in, pulse spreading is going to spread those pulses out, and they're going to be overlapping with one another, and that's going to cause give us an upper limit on the bit rate of the system. So what I've got here is I've got a spreadsheet that shows a lot of sine waves plotted, and I've got a time axis here in this first column. And what I'm doing over here is I'm plotting multiple columns of sine waves at various frequencies. And this sine wave here is at a frequency of 0.1, this sine wave is at a frequency of 0.2, 0.3, 0.4, 0.5, and then it jumps all the way up to a higher frequency of 1. And instead of plotting the sine waves themselves at these increasing frequencies, I'm plotting a smoothed version of them. And so each point in the smoothed curve is the average of the values in its neighborhood time. So all these values that I circled are averaged to give this value. And then that running average is calculated throughout the whole curve. And I do that smoothing for all of these sine waves. And that smoothing is effectively behaving like the pulse spreading. Okay, so it causes each input piece to be spread out, and so now this value comes from all of these values. Okay, so this is characteristic of the pulse spreading, and it's also characteristic of the way real systems behave. And so what I've done down here at the bottom is I've plotted those sine waves. At the bottom is the original sine wave, which is, well, it's just the smoothed version of the original sine wave with a frequency of 0.1, and you can see that essentially its amplitude is still 1. Okay, the sine wave had an amplitude of 1, and so does this one. And that's because I'm smoothing over about 1 second's worth here, whereas the period of this sine wave was 10 seconds. Okay, so I'm smoothing over about 1/10 of a period. Now, as I go to the higher frequencies, you can see as I go up on these different sine plots, I'm going to higher frequencies. But you can also see that the smooth version of the sine waves have decreasing amplitudes as I increase the frequency. And finally, when I pop up to a frequency of 1, the amplitude is very low. Why is that? Because what I'm doing is I'm effectively taking this point as the average of points that are averaged over multiple periods of the frequency. And you can see then that when I average over multiple periods, I'm going to get something very close to 0. And so this simple model of a smoothing out, that is a pulse spreading type model of the system, really does give us this frequency dependent output amplitude from the system. I've also shown here in the plot, I've got my time axis, and in this column, the second column over, I've got impulse responses. I've got a whole bunch of zeros, then a 1, a whole bunch of zeros, then a 1. And you can see those pulses plotted as these spikes here in this graph. I also show the smoothed version of that, where each point is the average, the running average of the points in its vicinity, and this shows explicitly that these spikes are spread out, and so that this sort of running average or the boxcar average type of calculation really does represent a pulse spreading type of phenomenon. You can see that these sharp pulses are now spread out in time in this spreadsheet. So I'll end this video here demonstrating the spreadsheet and showing that indeed we do have, in general, we have P naught as a function of F, P naught prime as a function of F. This is the output power, is a decreasing function of F. Okay? And so I will leave it there, and I'll pick up on these slides in the next video.